Hey everyone, this is a quick video on a question that got asked, which is if you have a sphere with two holes drilled through it, what is the leftover volume? So I thought I'd do this special case and then talked about other cases that you might encounter and how those would go differently. So this one we have a sphere of radius 10. It's got two holes drilled through the center. The holes are perpendicular to each other. And I should also mention they also have radius 9 or radius 3. So the equation will have a 9. So I'm going to change that real quick. And then we want to know what is the volume of the sphere that is left over. So when you're working on that, the approach that I'm going to take is we have a volume of a sphere, right, that we can find. And we have two holes which are essentially the same because they have the same radius that are drilled through the center. We can find the volume of those. And then there's this intersection that we will basically be counting twice. So when I subtract one drill hole, subtract the other drill hole of the same volume, we'll count that intersection twice. So we'll have to add that back in and find what that is. So that's the approach I'm going to take on this one. So the first thing to look at is, think about is, where do you want to start, right? So I'm going to just take a quick look at the drilled components. So these two right here, I'm going to hide that sphere a second. So if you look at the drilled components, let's go make that a little bit bigger. You'll notice the end cap on there is not going to be flat as long as you're zoomed out enough, right? So you can see there's this little rounded part up here where the sphere is that when the hole gets drilled through, you have flat sides up until a certain point, and then you have kind of that rounded cap that's right there. So you can't use a standard volume of a cylinder on this one. You'll have to use something else, and the dome of that cap will kind of depend on the radius of the sphere that you're using. In this one it's 10, but if it's 12 or 15 or 20, it'll be slightly different. But what we can do on the cylinders is we can basically just use the volume between the top and the bottom of the sphere, and enclosed by that equation for that red region, which is going to be, since it's a circle of radius 3 going down, just x squared plus y squared is 9, if we want to look at that. So looking straight down, right, on our xy plane, this would be x squared plus y squared is 9 for that radius 3 circle. So I'm going to kind of hide this intersection for a minute and just look at that part. In Desmos, there are surfaces and volumes. Volumes you basically can't see through. Surfaces you can if you make them translucent. So I may adjust those here in a second. But the calculation for that is right here, this volume of a cylinder. Right, so essentially we're going to have two of these. Because I got both of these guys right here. So let's go ahead and go through what this is saying. Actually that 2 is something different. So this 2 is because I have this square root as my surface, the top, and I'm thinking of the bottom as 0. So going from 0 to that top and then doubling it for kind of that whole surface that's right there. So we're going to do that, and then so I'm just thinking of what is the volume under this surface that's at the top to my xy plane that's right here, and then I'll double it at the end to get the entire volume of that red cylinder. So I got the square root of that 9 minus x squared minus y squared, right? So and this actually should be slightly different. This should be our big sphere, right? So this should be 100, so I'm going to modify that. And then the bounds are going to be this negative, so this is solving for z, right? If I want to solve for z on that sphere that's right there, basically just find that little patch, right, as my top surface. Z is going to be that 100 minus x squared minus y squared. So that's where that comes from. And then I'm going from, if I'm doing a dy dx, the y's are going to go between the sides here of that circle. So that is going to be my solving for y, right? In the circle, I get this negative square root of 9 minus x squared for the left side, square root of 9 minus x squared for the right side. So those are going to be the left and right sides of that. And then the x's are going to go from negative 3 to 3, right? So just negative 3 to 3 front to back on those guys. So those are the bounds that'll fill in that circle and then go all the way up here. You could also, if you wanted, do these in polar, but I just left them in terms of x and y because of the intersection that we'll be doing next. So yeah, you could also convert those to polar if you really wanted to. But that is the volume of a cylinder. With that, right, like I said, top half or top cap and bottom cap as part of that sphere. So you wouldn't be able to use the volume of a normal cylinder to get that guy right there. Once you've got that, then it's kind of time to focus on the intersection. So I'm gonna hide these and show these again so we can focus on that intersection. So when I'm looking at these, right, right in here, I'm going to zoom this in a bit more. That intersection is kind of a weird shape, right? It's kind of hard to tell looking through. So from one direction, right, it's enclosed by a circle. From another direction, right, with the Z, it's also enclosed by a circle. But from here, it kind of looks like it might be squarish shaped. So I'm going to go ahead again and show a couple of these, not those two, a couple of these guys down here. I've already put in, and we'll hide the big cylinders. So these are going to be the parts of the cylinders. If we want to look at, say, how one of these compares to the other. So this is like the red cylinder going up, and the sides that are part of that intersection are just going to be shown in that yellow color. And then for the blue, right, we have this cylinder going sideways, and the intersection is just going to be this guy right here. So what I want to do is I want to stay in between all of those surfaces for this guy. So looking at that intersection, right, I've kind of drawn in, we can think of adding up these squares. If I'm thinking from the x direction, right, just looking straight on, these are all going to be squares. I even got this slider A. If I adjust that, I can kind of see, right, that square is going to go really small and then kind of add it up. So this is sort of the volumes by slicing type of idea from Calc 2. So what we're going to do is, again, do an integral. We can do a double integral even with this guy, but really it's not totally necessary because this is a square. So as long as I can get one edge of the square, then I just need to multiply it by the height, and then the dx, if I want to use that x as that thin direction in the x direction. So a thin piece in the x direction. So let's see, we got from here to here, right, will basically be along the edge of these cylinders. So we're right on the edge of the cylinders with all of these pieces. And so I've got this guy right here. Normally we would have that square root of 9 minus x squared if we solved for either the y or the z, either one. But then we're going to square it because we have a square, right? So volume of a square, we got that length. That's going to get squared. So that square root will get squared and just leave us with the 9 minus x squared. So there's that piece. And then we're going from negative 3 to 3 in the x direction. So both of these pieces, right, both the y and the z, because the cylinders match up, we are going to get those squares, and we can just add that across the x direction from negative 3 to 3 just that 9 minus x squared dx. So that's kind of it. So there's my volume of the intersection. We've already finished the volume of the cylinder pieces, and then we just need to put them all together. So volume of sphere, I got that 4/3, right, pi r squared. So that's there. We got the volume of the cylinder, so that's the 552. So we're subtracting that out, right, twice. And then I just need to make sure I add back in one of the intersections, because we subtracted the intersection twice. With both cylinders, I need to put one of them back in. So adding that back in, then I get this 3119 number that's right there. If you're wanting exact values, these integrals you can compute by hand, right, get some exact values. Or sometimes, right, you can even fudge a little bit, like take this number here, go down, and if you think it's something in terms of pi, right, divide by pi. That doesn't give me a super nice number, so might not work on this one, but sometimes it works where you'll get like a nice number like 36.9999, and then it's 37 pi or something like that. But occasionally, right, it's maybe also something involving roots or something like that, and then it's kind of hard to tell. So if you wanted exact values, then yeah, you would have to go through this by hand and go through. But if you're just looking for an approximation, setting up the integral in Desmos and then computing it out is a good way to go. So a couple of variations that could happen that we'll talk about before I end the video is if I'm showing these guys, and I'll go and hide that intersection now on the sphere, right? So here's our sphere, zoom that out a bit, and there's our intersecting pieces, right? There's a couple things that could happen. One is your spheres are off center, right? So and then the other is the spheres are different radii. So if I just make, say, this x squared plus z squared, right, at 25, all of a sudden now this is a much larger cylinder. It's still centered, right, with the center of the sphere and everything else, but that intersection you would find differently, probably with an integral rather than, or a double integral rather than the way that we did it before with the squares, because these are no longer going to be squares in those guys. So that would change, but you could still do the same approach of volume of the sphere, find the volume of each. This time each cylinder would have to be computed separately, right, and then add back in that intersection that's right there. So kind of the same approach as a whole, but several different computations going through. You could also have spheres that are off center, right? So that could also be something that happens, right? If this were, we'll keep the same size for now and just say move one of these. So maybe this is a y minus 1, right, squared, and that gets moved over. In that case, right, it doesn't really look any different, but the top and bottom would be different. So the intersection would remain the same, but that top piece and bottom piece would be different because now we have a different cap on our cylinder for those. So you can still find it the same way with that integral. You would just want to make sure that that sphere or your cylinder, either one, is offset on the bounds of that integral. And then the other thing is, right, these could be even something where, let's say we make this radius 4, and let's make this a radius 1, and we'll adjust this by a bit, right? So we got x, let's say minus 5 squared, right, something like that. And in this case, our two drill holes don't even meet, right? So we got one through the center there vertically, and then we got another one over here, but it's offset and doesn't even intersect the other one. Or it could be maybe even these cylinders partially intersect and partially not. All right, well, one doesn't go all the way through the other one, but they kind of meet up a little bit. So there are just a whole lot of scenarios to consider whenever you're doing these. So you would want to be very careful when you're reading the directions to know what kind of setup is happening with those two holes. So anyway, hope that was a little bit helpful. And this is kind of the approach when you have complicated situations. It's to think about the different components, how they interact, what is going to be in common, what is going to be different, right, if things change slightly. So hope that helped, and see you in the next video.